Hello friends, in the second lecture of structure of atom, we are going to discuss about the discovery of electron, protons and neutrons and specifically the experiments regarding it. So let's start with the very first experiment, that is the cathode ray experiment, and this experiment was given by J.J. Thompson. Now, what was the setup of the experiment? Let's see this. The setup of experiment was something like this. Okay, over here, the very first thing that you could notice is a tube, and this tube is referred as Crookes tube. This tube is called as a Crookes tube, and over here, what we need to understand and what we need to remember very carefully is in this Crookes tube, we have taken a gas at very low pressure and a very high voltage. Now, very high voltage means how much high voltage? The voltage is around 10,000 volts. And if you notice in the diagram, your tube, the Crookes tube, is connected to a vacuum pump. And why is it connected to a vacuum pump? Because I need to maintain the pressure at 0.1 to 0.01 atmospheres. So, how much low pressure is required for this experiment? The pressure which is required is 0.1 to 0.01 atmospheres, and the potential difference is of 10,000 volts. Also, if you notice, there is one green glow in the diagram, right? Now, why this green glow occurs? It's because you have coated your tube with a ZNS screen. Now, what is the speciality of ZNS screen? The speciality is that this ZNS screen, it would start glowing, or you would see sparks when any charged particle hits the ZNS screen. And therefore, we have coated this entire tube with ZNS, that is zinc sulfide. Okay, so now J.J. Thompson performed this experiment and he found out certain properties of cathode rays. So what are the properties of cathode rays? Let's understand. The very first property, cathode rays travel in a straight line. If you notice the diagram, they are originating towards cathode, migrating towards anode, and yes, they are doing this in a straight line. So please remember this, cathode rays travel in a straight line. Moving on further, they exert mechanical forces and thus they are mechanical particles. Now, how did J.J. Thompson come to know that they are mechanical particles or they can exert mechanical force? It's because what did J.J. Thompson do now? He observed, or first thing, he kept a pinwheel over here in the path of cathode rays. Now, this pinwheel, the very first thing what he observed is that you are getting a shadow of this pinwheel. And whenever you get shadow of anything, you say that light is traveling in straight line. So if light travels in straight line, it gives you a shadow. That means even cathode rays are traveling in straight line and therefore it is giving you a shadow. That's point number one. Point number two, what he observed that this pinwheel started to move after some time. And if your pinwheel is moving, that means it has been exerted by some mechanical force. And what is that some mechanical force? It's nothing but your cathode ray particles. Moving on further, what did J.J. Thompson do? J.J. Thompson first observed that these cathode rays are moving from the negative terminal towards the positive terminal. Now, if anything gets attracted towards positive terminal, that means the something or that particle is nothing but a negatively charged particle, because we know opposite charges attract each other, whereas like charges repels each other. Okay, the next point, they have heating effect. Now, how do you observe that they have heating effect? What did J.J. Thompson do? He replaced this pinwheel. Okay, so this pinwheel was replaced by a small metal block. And what he observed that after you put on the experiment once again, this metal block started to heat up. And if this metal block is heating up, that means I can definitely say your cathode rays or your cathode rays particle have heating effect. So let's move further. The last point over here, they have very high penetrating power because they are able to penetrate the metallic anode in front of the ZNS screen. Acha, tum notice karo, dekho, let's see over here. You have a ZNS screen and before the screen or in front of the screen, you have a metallic anode. Now, if the cathode ray particles are going to come, what is going to happen? First, they are going to strike the metallic anode. From this metallic anode, they would penetrate and then strike the ZNS screen. So if you're saying that your particle is able to strike and you're getting a green glow, That means your particle has a very high penetrating power. And therefore you say that yes, cathode rays have very high penetrating power. Let's move further. Now, moving over here, we need to understand one very crucial thing. That is, what is the source of these cathode rays? The very first thing about the source, the very first source over here is the metal of cathode. Whatever metal you have taken, it might be steel, it might be copper, it might be any metal precisely. Okay, so the very first source is the metal of cathode, and the second source is the gas particles that you have taken. Now, how is this happening? Let's understand. Okay, let's imagine you have a tube, something like this. I'll just magnify the diagram for you. So you have a tube, and in this tube, let's suppose you have a cathode over here, and this cathode is connected to a very high potential difference. So I'll just write over here high potential difference. Okay, now what is happening? Because your battery is giving you a very high voltage, so the electrons in the cathode, they get excited. And whenever the electron get excited, what would happen? This electron would start moving towards the positive terminal because electrons are negatively charged. Okay, so let's move further. Now, when this electron is moving from the cathode towards the anode, in between, they would observe certain gas particles. So here you have gas particles. And now what is going to happen? Let's see, a very, very important scenario. This gas particle, now let's suppose you have a gas particle over here and an electron is coming by. This electron strikes the gas particle and dislodges one more electron. So what is going to happen? तुम्हारे पास starting में एक electron था. This one electron is going and hitting the gas molecule and dislodging one more electron over here. So now from one electron, you got two electrons. Now these two electrons would start moving further. They would again encounter a gas particle. Again, one more electron would be dislodged. So from 2, you would get 4. From 4, you would get 8. And likewise, this would keep on happening. So therefore, what we can say is the very first electron that you observed was from the cathode, from the metal of cathode. And after that, all the subsequent electrons that you observed or all the subsequent electrons that you obtained were from the gas particles. Okay, moving on, because your gas particles are losing electrons. And if they lose electrons, they should definitely be positively charged. So what would happen in due course of time is that all of your gas particles would start gaining positive charges. And this process in which a gas or any particle or any atom gains a charge, whether it would be a positive charge or a negative charge, is referred as a process of ionization. So what we can say over here is your gas in the cathode ray tube is undergoing a process of ionization. And why is it undergoing a process of ionization? It's because one electron from cathode is moving with a very high velocity towards anode. While doing that, he is encountering a gas particle, he is hitting it, dislodging one more electron, and then again it starts the process. So 2 se 4, 4 se 8, and it will just keep on happening. Okay, so let's move further. Now, the next question comes is, how do you prove that these particles that you have obtained, the cathode ray particles or the electrons, how do you prove that these particles are fundamental particle? Okay, I know a very basic stuff is, let's suppose if you talk about human beings, all the human beings have 2 eyes, 2 ears, 1 nose, 2 hands. So basically, can I say that 2 hands, 2 eyes, 1 nose, 2 ears are nothing but fundamentals of a human being, correct? Similarly, what did J.J. Thompson do? He had taken many different gases, and what he observed that every time you take a gas, it might be a mixture of gases, it might be a single gas, every time you take a gas, you would get the charge to mass ratio, which is 1.758 into 10 raised to 11 coulomb per kg. So what he did a series of different experiments, and possibly somewhere around 350 different experiments or 350 different types of gases. But every time he used to get this same number over here. And if he's getting that same number, that means, can I say that this particle, whatever you are dealing with, is a fundamental particle amongst all the atoms or amongst all the elements? And therefore, you say that this particle, which is nothing but cathode ray particle, which we now call this as electron, this electron would be referred as a fundamental particle. And why it would be referred as fundamental particle? Because every time you take any different atoms or any different elements, you would always get the charge to mass ratio which would be same. Okay, so this is therefore referred as a fundamental particle. Moving on, let's see the next one, that is proton. So for the discovery of proton, the experimental setup is almost alike like the cathode ray tube experiment. The only difference, however, listen to this. The only difference, however, is you don't have a normal cathode. You got something called as a perforated cathode. And we'll see why is this so. Okay, moving on further. Again, I have a Crookes tube. I have connected it to a very high potential difference, that is again 10,000 volts. I have connected it to a vacuum pump, and because of that I have a pressure of somewhere around 0.1 atmospheres. Everything happens same. The only difference now, you talked about cathode rays, and while talking about cathode rays you observe that yes, your gas undergoes a process of ionization, because of which your gas would definitely get a positive charge. Now, because he is getting a positive charge, what would happen is that these gas particles would start moving towards the cathode. And these gas particles which are positively charged, which are moving towards cathode, are referred as anode rays. But then, cathode rays, unlike cathode rays have very high penetrating power, so they could just penetrate your anode and then strike the ZN screen. However, cathode rays don't have sufficient penetrating power. And because of this, what you need to do is, you need to drill certain holes in your cathode. And therefore, we require a perforated cathode. So the very first point over here, which you have suggested right now, is cathode rays are having high penetrating power, whereas anode rays that we are going to study would be having very low penetrating power. Again, let's talk about the properties, but before that, who did this experiment? This experiment was done by Gold Stein. Okay, so Gold Stein did this experiment. Moving on further, what are the properties of anode rays? The properties of anode rays, the very first one, they travel in straight line. Like cathode rays, even anode rays travel in straight line. Moving on, they are positively charged because obviously they have to be the opposite of cathode rays, right? Next one, they are material particles and exert mechanical force. So if you keep a pinwheel in between, that pinwheel is still going to move. Further, they have heating effect. Just remember, the heating effect of cathode rays is slightly less as compared to the anode rays. Okay, moving on further, they have low penetrating power and produces sparks or scintillations when striking on a ZNS screen. Now, over here, scintillations is just meaning of sparking. That's it, nothing more than that. Okay, again, what are the source of anode rays? The source of anode rays is only the gas particle. Please remember this. The source of anode rays is only gas particle, and it's not the material of anode or cathode. Okay, let's move further. Next thing is discovery of neutrons. Okay, before we start discovery of neutrons, we just need to understand few different stuff. If you remember, in the first module, we talked about Dalton's atomic theory, and over there we said that atom is neutral. Therefore, what we know is, jitne electrons honge, the number of electrons would always be equal to the number of protons. Okay, but then it was found out by Chadwick that this doesn't happen. Let's see what. So what did Chadwick do? Chadwick took a beryllium film and he started bombarding this beryllium film with alpha particles. So over here, this is alpha particle. And what did he observe? He observed that this beryllium, which was earlier 4,9, now gets converted into carbon 612. Over here, if you just consider the entire reaction, let's check. Okay, first of all, 4 plus 2 gives you 6. That's definitely right. And yes, therefore, can I say the atomic number is conserved? Nothing has changed over there. But then, let's look at atomic mass number. There is something happening over here. Okay, let's check. 9 plus 4 actually gives you 13. But over here in carbon, it's only 12, right? So therefore, can I say that there has to be a particle which is not contributing anything towards atomic number, but is definitely contributing something towards atomic mass number. And this particle, which is N01, is now referred as neutron. Okay, so please remember, neutron is a person who would have no charge. That means neither positive, neither negative. He won't be contributing anything towards atomic number, but definitely he would contribute towards atomic mass number. And who did this experiment? It was done by James Chadwick. So, the discovery of electrons was done. So, the discovery of electrons was done by who? It was done by J.J. Thompson. The discovery of protons was done by Gold Stein, and the discovery of neutrons was done by James Chadwick. Okay, let's try to compute everything, whatever we know as of now, into a tabular format. So, this is your table. What all things we need to understand over here? Something very, very important. Let's see. The very first thing that we'll be discussing about is obviously the fundamental particles, and then we will be discussing about who discovered them, what is their relative charge, what is the absolute charge, relative mass, and absolute mass. Let's see. Before starting on, understand, whenever you would solve problems, okay, you would always use absolute charges and absolute masses. Okay, relative charges and relative masses are only used for representations. Like for example, you have been studying from your lower grades that protons have plus charge, +1. Okay, but they do not actually have +1 charge. They have something else. Okay, but then you're always representing this as +1, electron as -1. Okay, you say electrons have a negligible mass. Okay, so you can neglect it out. But how much exactly? Okay, and while solving the problems, I can't neglect the mass of electrons, right? So therefore, what we need to remember, absolute charges and absolute masses would be used while solving problems. Relative charges and relative masses would be just used as a source of representation. Okay, let's move further. The very first thing, electron, discovered by J.J. Thompson, the absolute charge is -1.6 into 10 raised to -19 coulombs. The relative charge is -1. Absolute mass 9.1 into 10 raised to -31. Relative mass is negligible. Similarly, let's talk about proton, discovered by Gold Stein. Now, what is the charge of proton? It is exactly opposite to electron, and that is +1.6 into 10 raised to -19 coulombs. Okay, what's the relative charge? It's -1. What is the absolute mass? Then the absolute mass over here is 1.67 into 10 raised to -27 kgs. Relative mass is 1. Moving on, let's talk about neutrons. The very first thing, neutrons were discovered by James Chadwick. The absolute charge is 0 because it's neutral. The relative charge is also 0. The absolute mass is exactly same like protons, and the relative mass is 1. Okay, finally, before wrapping up this entire module, just remember a very, very important note. And the note goes something like this. We need to remember that mass of 1837 electrons is equal to mass of 1 proton. Okay, and because mass of 1 proton and mass of 1 neutron is absolutely same, we would say this could be also written as mass of 1 proton or mass of 1 neutron. Okay, so if anybody asks you what is mass of 1 neutron, you can definitely say it's equal to the mass of 1837 electrons. Okay, or I could simply say 1 proton is 1837 times heavier than an electron. So with this said and done, we would stop over here for today and meet in the next module with the problems related to the charge to mass ratio. Till then, thank you students.